Have you ever really stopped to wonder how we measure the world around us? I mean, think about it. From the phone in your hand to the building across the street, everything has a shape, a size, a volume. Well, today, we're diving into mensuration. It's basically the geometry of everything, and we're going to give you the tools to see and measure our world in 3D.
Just look around you for a second. You've probably got a can of soda, maybe a basketball, or a party hat from a birthday. They look simple, right? But they're actually little geometric puzzles. How much paint would it take to cover that can? How much air is actually inside that ball? These aren't just math class questions. They're real-world measurement problems.
In the language we use to solve these puzzles, it's called mensuration. It's the part of math that lets us calculate everything from surface area to volume. You can think of it as the official rulebook for the physical world. So yeah, let's get into it.
So here's our game plan. We're going to start by seeing our world in 3D, then we'll build our toolkit of essential formulas. After that, we'll put those formulas into action, learn how to combine and even slice up shapes, and by the end, hopefully change the way you see everything around you.
All right, first things first, our world in 3D. See, before we can measure anything, we have to learn to see the basic shapes that make up our world. These geometric solids, they are the absolute foundation for everything else we're about to do.
And that brings us to our basic shape toolkit. Think of these formulas as the keys that unlock the secrets of these fundamental shapes. And don't worry, this isn't going to be a boring list. We're going to see why they work. This is where you get your power tools. Let's start with the basics of the basics, the cuboid and the cube. You know, a box. For any cuboid, the volume is just its length times breadth times height. Super simple. A cube is even easier. Since all the sides have the same length, its volume is just that length cubed. It's simple, but so powerful.
Next up, the cylinder, your classic can of soup. Its volume is just the area of the circle on the bottom, that's pi r squared, times its height. But here's the really cool part, the curved surface area. Imagine you could peel the label off the can and lay it flat. What would you have? A perfect rectangle. Its height is the can's height, h, and its width is the distance around the circle on top, which is 2 pi r. Isn't that wild?
Now, the cone. And here's a great little secret. A cone's volume is exactly 1/3 of a cylinder that has the same base and height. But to measure its surface, we need something new, the slant height, which we call L. That's just the diagonal distance from the pointy tip down the side to the bottom edge. It's basically the hypotenuse of a right triangle made by the radius and the height.
And finally, the beautiful perfect sphere, and its other half, the hemisphere. A sphere's volume is 4/3 pi r cubed, and its surface area is exactly 4 times the area of a circle with the same radius. So what about a hemisphere? Well, you just cut those formulas right in half. Simple as that. And there we have it. Our toolkit is officially complete.
Okay, so we've got our tools. Now, let's actually use them. In this section, Formulas in Action, we're going to apply all this knowledge to solve some real, tangible problems. This is where the theory gets its hands dirty. So here's our first challenge, a classic joker's cap. We're told its radius is 10 centimeters and its height is 21 centimeters. The question is asking for the amount of cloth we need. That's a clue. It means we need to find the curved surface area, basically the pointy part, not the flat bottom circle.
The key here is to follow the process. First, what shape is it? It's a cone. What formula do we need? The curved surface area, which is pi rl. But hang on, we have r and h, but we don't have l. No sweat. Step 2 is finding that missing piece. We use that little Pythagorean trick to calculate the slant height, and once we have L, we just plug everything in and solve. It's just a puzzle, one step at a time. Now, while that cone problem had a couple steps, sometimes it's much more straightforward. If you have a simple cuboid oil can, you just multiply length times breadth times height. Boom! 20 times 20 times 30 gives you 12,000 cubic centimeters of volume. Simple, direct, and super useful. But what happens when things get a little more complicated?
Because, let's be honest, the real world isn't always made of perfect, simple shapes. Usually, things are combinations of shapes or even slices of them. And that's exactly what we're tackling next, combining and slicing shapes. This is where it gets really fun.
Think about a circus tent. It looks kind of complex, right? But if you really look at it, you'll see it's just a cylinder on the bottom with a cone plopped on top. So to figure out how much canvas you need, you don't need some crazy new formula. You just find the curved surface area of the cylinder part, find the curved surface area of the cone part, and add them together. You see, complex shapes are usually just simple shapes in disguise.
Okay, now let's take that idea one step further. What if you take a cone and just chop the top off, with a slice parallel to the base? You don't just have a cone anymore, you actually create two things, a little mini cone on top and this brand new shape on the bottom. And that new shape has a name. It's called a frustum.
And a frustum is one of those shapes that once you know what it's called, you start seeing it everywhere. A bucket, a lampshade, most drinking glasses, they're all frustums. It's probably one of the most common shapes we use every single day, and it's just born from slicing up a cone. It's not some scary new thing, it's just a piece of something we already get.
And of course, the frustum has its own special formulas. And yeah, they look a little more complicated than a simple cones because now we have two different radii to worry about, R1 for the big base and R2 for the small top. But the principles are the exact same. We still have ways to find the slant height, the surface area, and the volume.
Wow, we've covered a lot of ground, huh? From basic building blocks to complex sliced-up shapes. So now we get to our final section, seeing in 3 dimensions. And this isn't just about the math anymore. This is about getting a new lens to view the world through.
So what are the big takeaways here? Well, first, that everything physical has a shape that we can actually measure. Second, that a few simple formulas are like the keys to unlock all those measurements. Third, that most complex objects are really just simple shapes put together. And maybe most importantly, mensuration isn't just a chapter in a math book. It's a real tool for understanding the world you live in.
Or to put it another way, the world is built from simple shapes. Your challenge is to see them. Once you start looking for the cones and the cylinders and the spheres and everything, you'll really never see your surroundings the same way again.
And that really brings us to the end. You now have the fundamental toolkit of mensuration. So the question isn't, how can you measure the world anymore? It's, what are you going to measure first?